Alright, so this last set of notes for the 7.2 is probability distributions. And we do a little bit with probability distributions here in Chapter 7. Remember, 6, 7, and 8 kind of build off each other. And so we introduce them here. We'll do a lot more with them in Chapter 8. Alright, Chapter 8 will be utilizing probability distributions more. But we will introduce them here. You still have to know how to do them here. And find them. And basically a probability distribution is just a representation of all possible outcomes in the sample space where we've listed them in a table. Right? So the simplest example would be if I flip a coin one time, I could get one head or two heads, right? Those would be the possible outcomes for heads, and the probability of that case. In those cases, and we'll do actually an example where we'll do that. We'll toss a fair coin 3 times and we'll look at all the different outcomes. So it's just a list of all the outcomes in experiments. So S sub I would basically be every single outcome possible in my sample. So my sample space, remember, is capital S. So the lowercase s just represents all the little outcomes. Then we list them. All right, what are all the things that can happen in my probabilities? All right, what are all a list of all of them, all my outcomes? And then with them, we pair in the second part of our table the probability of each of those outcomes. Right? Probability of each of those outcomes in my universal set. In order to be a probability distribution, 2 things have to be true. Every individual probability has to be less than or equal to 1, meaning there's only one outcome, right? The probability is 1. So, or if there's multiple outcomes, they're between 1 and 0, but each one of them have to be less than 1 and greater than 0. No negative probabilities and nothing bigger than 1, right? They're all smaller than 1 or greater than 0. The second thing that's, again, important, and we'll actually use this a lot in the next chapter, right? We'll use it a little bit in this chapter. It's actually an important, sort of, like I said, key concept about why probability distributions are useful. If I've listed every possible outcome in a sample space, right, and then I found the probabilities of each individual outcome, well, if I run the experiment, one of those have to happen, right? And so it's 100% of the outcomes, right? And when I add them up, all of my probabilities in my sample space should add up to 1, and exactly 1. No more, no less, right? So they should be, those are 100% of the outcomes, 100% of the cases, and so the probability is 1. One of those outcomes will happen when I do the experiment, all right? And so I've listed all the possibilities, and so all the possibilities should add up to 1. And again, we use this concept. Sometimes what they'll do is they'll give you a probability distribution table, and they'll leave off one probability, and you'll use the fact that, well, I know all of my probabilities have to add up to 1, so if I add up the ones that they've given me, and I subtract them from 1, that has to give me my missing probability. That's one way we use this. And then other aspects too. We'll get to an example today where we'll actually set up an algebra equation to help us find the probabilities based on the fact that my probabilities in my distribution should add up to 1. All right, we'll do an example of that. All right, so that's a big thing. Right, all the probabilities in my distribution have to add up to 1. And then the third thing is an individual event, which means if I'm not looking at the entire probability distribution, but I'm looking at an event, all right, probability. So if I'm rolling dice, all right, all of my outcomes would be 1 through 6, but suppose I'm looking at the event, I only want even numbers, all right, my event would be adding up the probabilities of each of my even numbers, right? Even number would be rolling a 2, a 4, and a 6. And I just add up those probabilities. That would be the probability of my outcome. All right, and so what it is, if I'm looking at it in a generic case, so these would be all of my outcomes in my sample space, probability of my outcomes. All right, so suppose there are 3. All right, so first event would be 1, second event would be 2, and third event, and then these would be the probabilities. First event, probability of my second event, probability of my third event in my universal set. All right, so we've broken them down by what can happen in my all the different cases. And so what we do, well, when we add these up, the sum of my probabilities, so these should all be fractions and decimals smaller than 1. When I add them up, if I add each one of these up, it should add up to 1 exactly. And so that's what we mean by probability distribution. And we're just going to practice that in a couple of examples. All right, the first example is the relative frequency case, right? And then the second example will be a theoretical case. And then the fourth example is going to be a little tougher case, and we'll get to that, and I'll talk about it when we get there. All right, so relative frequency is always the easier one, right? Relative frequency probabilities are just easier than theoretical probabilities. I suppose that we have gathered a large class of 250 students. The professor computed the grade point average, the percent, for each student who's earned the class and recorded it in a relative frequency table. All right, we want to find the relative frequency probability distribution for this particular table. All right, so the frequency is the outcome. These are all of my events, right? So my events would be I get an A, a B, or a C, and then these are the frequency of my event. All right, so this is the group. Event getting an A, event getting a B, event getting a C, and event getting a D. All right, so these are my outcomes. All right, I get A, B, C, D, or F. Frequency is what I'm going to use to find my probability. I want the probability of my particular outcome. So what's the probability that I have a student with an A? What's the probability of a student with a B, C? And so I'm looking for probability there an A student, probability there a B student, probability there a C, and so on. Right. And those are all of my probabilities. All of my outcomes possible, along with their probability. And we find the probability using the relative frequency table, where we take the frequency divided by my total, which my total is 250 students. And so that's it. It's just for each probability, well, how many A's out of my total, how many B's and C's, and so on. And so the probability is just, well, I've got 45 chances to pick an A student out of 250. And I'll find the decimal in a second. I'm just going to write these out. B would be there 60 chances out of 250. C would be 65 chances out of 250. D, 50 chances out of 250. I'm getting a little sloppy. And then F would be 30 chances out of 250. Right? Then I'm going to find the decimal, because these actually all come out to fairly nice decimals. All right, so you divide the 45 A students by the total 250, and that comes out to 0.18. 60 divided by 250 comes out to 0.24. 65, 0.26. 50 divided by 250 comes out to 0.2, and then 30 divided by 250 comes out to 0.12. And there's my probability table. Right? These are my outcomes, and then this is the chance they'll happen. Right? So there's the outcomes, probability of the outcomes. And if you added up all of the outcomes, if you take the sum of all of the probabilities, it should come to 250 out of 250. You add up the fractions, or if you add up the decimals, it should also come up to 1. It's 100% of the students, right? If you think about it in terms of probabilities. 18% have an A, 24% have a B, 26% have a C, 20% have a D, and 12% have an F. If you add up all of the groups, it's 100% of the students, right? The probability, if I randomly select a student from this group, they've got to land in one of those. So it's a 100% chance they're in one of those groups. And so the sum should always add up to 1, and it does, right, in this relative frequency probability. All right, so there is my probability distribution, right, which, again, we kind of ignore the frequency. It's the outcomes and the probability of my outcomes. And now questions. So basically we get probability distributions, which are all possible outcomes, and then what we'll typically do is ask you questions on them, events that occur based on my probabilities in my distribution. Alright, so suppose we want to find the probability that if we randomly select a student from this particular class, the student has a 70% or better. Alright, so 70% or better, which would mean they land in one of those three groups. Alright, the event is that they have a 70% to 100%, right, or better. So the probability of my event, probability they have a 70% to 100 or better, right? Well, it's the add up all of the different cases. If they're in the C group, B group, and A group, right? And those are mutually exclusive events, right? You're an A student, you're in the A group. You're a B student, you're in the B group. If you're a C student, you're in the C group. You can't be in both groups at the same time, right? So they're mutually exclusive. Since they're mutually exclusive, I just add up all of the cases. So I just take the probability they're an A plus the probability they're a B plus the probability they're a C. Well, probability they were an A student was 0.18. Probability they were a B student was 0.24. And probability they were a C student was 0.26. Add up all of the outcomes, so 18%, 24%, 26% adds up to 68. So 0.68 is the probability, right, or 68% of the students had a 70% or better. All right, but they did ask for the probability. Probability is always written as the decimal. All right, so the decimal is 0.68. We usually talk about it in terms of percents if you want to think about it in terms of percent chance. So I had a 68% chance of selecting a student with a 70% or better. Right? The probability is 0.68, the decimal 0.68. Right, the second question is actually the complement to that. The probability that we randomly select a student that got a D or F. Well, that would be the opposite of getting an A, B, or C, so that's this group. And there's two ways to do it. You can either add up the two cases, or it's the complement to the previous event, so you could take your 1, subtract the 68, and either way's the same. Probability they get a D or F would be our 0.2 plus our 0.12, right? D 0.2, F 0.12, and so it comes out to, make sure I double checking myself, making sure I wrote the numbers down right, 0.32, right, which again was the complement to that, right? 68% of the students have an A, B, or C, 32% of the students have a D or F. So the probability of randomly selecting a student with a D or F, probability is the decimal, 0.32. If you think about it in terms of percent, it's a 32% chance. All right, so that's a relative frequency probability distribution case. This next one's going to be a theoretical case based on rolling a fair coin 3 times. Alright, so rolling a fair coin 3 times, record the number of tails that occur. Alright, so there's two ways I could have drawn the probability distribution. Probability distribution, you have to base your outcomes on whatever it is you're looking at. Alright, so I chose to look at tails. Right, heads are buried in there, but I have to pick an outcome that I want to choose to write as my events. Alright, so my event that I'm looking for is I'm figuring out, well, how many ways tails can occur. So record the number of tails. Alright, so construct the probability distribution. Alright, I'm actually going to list the universal set to remind you what the universal set is, so I could get all heads. We've done this now a few times, so I'm just going to list it fairly quickly. So bear with me for a second while I list all of these outcomes. There should be 8, so hopefully I've got all 8 outcomes. Alright, we're counting tails. Alright, so when I draw out my probability distribution, and I'm going to draw it sideways like this because it's just a little easier to draw on my tablet that way. Alright, so up top is my outcomes. Well, the outcomes I am going to count is the number of tails in 3 tosses. Right, probability of my outcomes. Well, how many ways can I get tails in 3 tosses? Well, I could get no tails, which implies all 3 came out heads, right? 0 tails. I could get 1 tail, right? 1 tail and 2 heads. 2 tails. or all 3 tosses can come out tails, right? Those are the outcomes. And buried in them is the heads cases, right? If I get 0 tails, that implies that I had 3 heads. If I get 1 tail, that implies I had 2 heads. If I get 2 tails, that implies I have 1 head. And if I get 3 tails, it's the outcome all 3 tails. All right, then the outcomes, probability. All right, so how many outcomes, what's the probability that I get 0 tails? Well, the probability of getting 0 tails is 1 out of 8, right? 1 out of 8, 1/8. Probability I get 1 tail. I got to figure out how many ways did I get 1 tail. There were 3 out of 8. Probability that I get 2 tails, 3 out of 8. And probability all 3 came out tails was 1 out of 8. Alright, I'm going to leave them the fractions because they're kind of nice, simple little fractions. I'm not going to write the decimal this time. I'm going to leave it 1/8, 3/8, 3/8, 1/8. Alright, so there's my probabilities. So probability of getting 0 tails is 1/8. Probability of getting 1 is 3/8. Probability of getting 2 tails is also 3/8. If you add them up, right, they would add up to 8 out of 8 outcomes, or 1, right? You'd add them up, you'd get 4, 7, 8, right? 8 out of 8 outcomes. So there's my probability distribution, my theoretical probability distribution of rolling a coin 3 times and looking at the outcomes that tails occurred, number of outcomes where tails occurred. Alright, then we'll ask you a question based on the probability. Using the table, find the probability of tossing no more than 1 tail. Alright, no more than 1 tail would be the outcome where I get 1 tail or 0 tails. Alright, these 2 outcomes. 1 tail or 0 tails. So probability no more than 1, if you can read that. Well, it would be the probability of having 0 tails plus the probability of getting 1 tail. Well, 0 tails was 1/8. 1 tail was 3/8. And this is kind of a reason why I left it this way. They're not decimals, and they're easy to add because they have the same base, right? 1/8 I can add to 3/8 to get 4/8. And then I'll write the decimal. 4/8 is 1/2 or 0.5. So there's a 50% chance if I flip a coin 3 times, I'm not going to get more than 1 tail, which means 1 or fewer. Alright, the last example is sort of a toughie. Right, this is the one where I'm going to use the fact, and actually I'm going to use a little algebra in the fact, that my probabilities will add up to 1. Alright, so we've got a dice that's not weighted fair, so it's an unfair dice. It's been weighted in such a way, so they put a weight in it, where it's been weighted in such a way that the 1 and 2 are 3 times more likely to pop up, to roll, as all of the other numbers. Alright, so all of the other numbers have the same likeliness, but they're 3 times fewer to show up than the 1 and the 2. Find the probability distribution. Actually, I have to in order to answer the question. Right, so I'm actually going to use the fact that the probability distribution adds up to 1 in order to find my probabilities, and then I'm going to use that to answer the question in part B. Alright, so first thing is to write out my distribution, my outcomes. Alright, so the outcomes, and then the probability of my outcomes. Alright, well, it's still a dice with 6 numbers on it. It's just weighted unfair. So I can roll a 1, a 2, a 3, a 4, a 5, and a 6. Maybe 2. Spread them out a little differently. 1, 2, 3, 4, 5, 6. Alright, now, I know that these 2 are 3 times as likely, right? Those are 3 times as likely to come up as the other numbers. So the rule of thumb on these type of problems is always start with what you know the least about. I know the least about the other numbers, right? The probability of rolling a 3, a 4, and a 5, and a 6. They all have the same probability, but I don't know what they are. Alright, so probability of rolling a 6, I'm going to let be equal to x. Well, the probability of 5 is the same as that, so that's going to be x. Probability of 4 is the same, and the probability of 3 is the same. So x means my variable, it's unknown. I don't know what the probability of rolling a 6 is, but I know the probability of rolling a 6, a 5, a 4, and a 3 are the same. So they're all that x value, whatever that probability is. And then I'll use that to write out my probability of rolling a 2 and a probability of rolling out a 1. Right? Because I know they're 3 times as likely. So if the probability of rolling a 6 is x, the probability of rolling a 2 is 3 times that. So it would be 3 times x. Well, the same thing with the probability of rolling a 1. It's 3 times that. So it's 3 times x. Right? And so this is where the algebra comes into play. I know the sum of all the probabilities equals 1. And I'm going to use that fact, and so I'm going to write that over here. So I'm going to write, I know the sum of the probabilities equals 1. Alright, well, I'm going to sum them up. What are the sum of the probabilities? Well, I'm going to add all of my x. How many x values do I have here? So I've got 1, 2, 3, 4, and then I've got 6, so I've got 10, right? When I add them up, there are 10 x values that represent all of my probabilities, right? I'm adding up all of these, so I'm just adding these. X plus x plus x plus x plus 3x plus 3x, right? It's the sum of all of those unknown probabilities have to equal 1, alright? So the sum of all the unknown probabilities is 10x equals 1, and then it's just a simple algebra expression. I solve for x. Well, I got to solve for x by getting rid of the 10 in front of it. I get rid of the 10 in front of it by dividing it out. And so the probability, or the x value, is 1/10, or 1/11th. 1/10, and you can leave it as the fraction, or you can write it as the decimal. I actually think it's easier to write it as the decimal. And so now I know what these probabilities are. They're 10%, 1/10. 0.1, this is also 0.1. 1. Those are 3 times x, so you take your x value of 0.1, multiply it by 3, and so that comes out 0.3, that comes out 0.3. You can always double check yourself. If you add up all of these decimals, it should add up to 1. It does. This adds up to 0.4. This adds up to 0.6. 0.4 plus 0.6 is 1. 100% of my outcome. All right, like I said, this is a toughie. It's a little weird. But once you've seen it, you should be able to duplicate it. And there is a homework problem that's similar to this, and there's a problem on the practice exam that's similar to this. Alright, so if you want to practice it, go try those 2 cases and look at those. Alright, so those are my outcomes. I needed this in order to answer the question. Right? I can't actually answer the question unless I've drawn out this probability distribution. So what's the probability if I've got this unfair dice, right? If I'm rolling this unfair dice where the 1 and the 2 are 3 times as likely, that I'll roll an even number. Alright, so probability that it's an even number. Well, it's the probability I roll a 2 plus the probability of rolling a 4 plus the probability of rolling a 6. Alright, rolling a 2 was 0.3, rolling a 4 was 0.1, and rolling a 6 was 0.1. So even with this unfair dice, there's still a 50% chance, 0.5, that you'll roll an even number. And like I said, this last one was a toughie. But once you've seen it, you should be able to duplicate it. And there's a couple practice problems you can go practice on your own. So there's one in the practice test like this, and there is one on the web-assigned homework. And you can go look at those and practice there. Alright, there is one that I do want you to try on your own with this set of notes. So you have 2 fair dice, a red dice and a green die. You roll them both at the same time. You want to record the sum of the pair. Alright, so remember, the sum means I add up the numbers in my pair. Alright, so a 3, 4 is a sum of 7, a 4, 3 is a sum of 7. Construct the probability distribution for the experiment, and then use it to figure out what's the probability of roll to sum less than 5. Make sure you do less than 5. Don't include the sum of 5. Just to kind of get you to set this up, alright, the outcomes, when you roll a pair of dice, there are quite a few outcomes. Read that. Alright, or events. probability of my events, which I'm going to leave those for you to find. But the events would be getting all the different sums. I can have a sum of 2, right? 2 is my smallest sum, up to, right, a 1 plus 1 is 2, up to a sum of 12. Right? So there's quite a few sums. There's 2 to 12 sums here. Alright, so you go 2, 3, and so on, all the way down to 12. Alright, so those are all my outcomes. And then you'd find the probability of those based on your how many ways to get a sum of 2. Well, there's just 1 out of 36. And so on, and all the sums in between. Alright, so again, this is the probability I'm asking you to set up on your own. Alright, so do make sure you go practice that, and then find the probability of getting a sum of less than 5. I will post the answer to this like I do always, once you're supposed to have finished watching this video. Alright, we'll stop there. That finishes up 7.2, the basic probabilities. Alright, basic probability of relative frequency, theoretical probabilities, and then putting them in distributions where we find all of the probabilities, either frequencies or theoretical. And basically the next few sections, 7.3, 7.4, is just going to kind of give you some more rules for probabilities, and then just practice these probabilities in the next few sections. Alright, so we'll wrap that video up there.